12 days from now, a 33 billion-ton interstellar visitor called 3I Atlas will dive past the Sun at 80 times the speed of a bullet, and that's where things could go wrong. Its path is nearly aligned with the solar system's traffic lane, the ecliptic, something no random comet should do, raising the unsettling question. Is this a natural wanderer, or a machine designed to break at the Sun and stop cold inside our system? While Earth's eyes will be blinded by the Sun itself, the only thing we'll know for sure is what emerges on the other side. The real danger lives in what we won't see when it matters most. If this kind of space mystery grabs you, subscribe now. We track every verified update from observatories and spacecraft so you never miss the moment truth breaks cover. 3I Atlas hurtles toward the Sun at nearly 55 km per second, threading a path that defies the odds. Instead of plunging in from a steep random angle, it skims the solar system's plane, tilted just to 5 degrees from the ecliptic, the invisible disk where planets orbit. For a visitor from interstellar space, random arrivals should scatter across the sky, most missing the ecliptic by wide margins. Yet here, the trajectory nearly overlays the planetary lanes, as if mapped to blend in with local traffic. Orbital simulations show only a slender fraction of interstellar objects arrive this way. The ecliptic is a thin belt on a vast celestial sphere. Hitting it within 5 degrees is like tossing a dart at a spinning globe and landing on a city street. The last two interstellar guests, Oumuamua and Borisov, cut in at high inclinations. 3I Atlas traces a nearly flat, retrograde arc. This alignment isn't a curiosity, it changes what's possible at perihelion. At perihelion, 3I Atlas will be moving at nearly 68 km per second, more than twice the speed of the fastest spacecraft humans have ever launched. That's the moment orbital mechanics offers a rare loophole: the Oberth effect. Burn your engines when you're moving fastest deep in a gravity well, and the same push changes everything. A 1 km per second change at 68 km per second isn't just a nudge, it's a hammer swing. Now imagine a retrograde burn right at closest approach, shedding enough velocity to transform a hyperbola into a bound orbit. The math is brutal. Dropping into a stable solar orbit near 1.36 astronomical unit could require on the order of 20 km per second of deceleration, far beyond messy, weak comet outgassing. So the test becomes simple to state, hard to pass. After the blackout, does the outbound track show a sudden step change that outgassing cannot explain? If yes, physics points away from nature and toward control. But we face a cruel constraint: the blackout window itself. During superior conjunction, every major telescope ground in space must look away. Hubble and JWST are hard-coded never to point near the Sun. Even TESS can't sneak a glance. The only thing we'll have is before and after. What happens in the furnace won't be witnessed, only inferred. Brightness told us 3I Atlas might tip the scales at 33 billion tons, but mass leaves fingerprints and Mars didn't feel a thing. In 2014, a smaller comet sighting Spring left a measurable tug on Martian navigation data. 3I Atlas passed at 29 million km and nothing. Not in MRO logs, not in ESA's trace gas orbiter timing, not in deep space network tracking. So either the mass is overestimated, its brightness inflated by dust, or an unusually reflective skin, or the structure is hollow or highly porous. Its rotation doesn't behave like a heavy chunk either. Photometry hints at a spin too tidy for rubble. And then the chemistry. Mid-September spectra logged a giant coma, 180, thousands kilometer across, with hydrogen cyanide venting at 4.5 into 10 to the power 25 molecules per second, about 2 kg of HCN each second, along with traces of water and CO. It looks natural, volatile rich, sun-warmed, shedding mass, until you stack all the oddities: low inclination arrival, retrograde lane keeping, negligible gravity signature, clockwork spin. Taken together, it reads less like debris and more like choreography. None of this proves intent, but it builds a baseline. If post-perihelion chemistry or motion changes in ways natural models can't replicate, that's when the story shifts. Here's the snapline. If 3I Atlas were engineered, perihelion is where you'd act. A fragile shell would fragment chaotically. A purposeful shell would deploy, releasing discrete units on controlled tracks like dandelion seeds in vacuum. each with its own small deltav. The evidence would be concrete. Post-perihelion, astronomers should see non-random fragment vectors, some accelerating away from the Sun, some steering, not just drifting. That's exactly the checklist the Galileo project teams prepared. Track every outbound speck, measure velocities, compare against breakup models. If it's random, engineering fades. If the sky paints straight lines and step changes, the implications are profound. Meanwhile, ExoMars TGO tried a long shot as 3I Atlas skimmed past Mars, turning its high-res camera off-planet for deep 5-second exposures. The frames came back ambiguous target 50,000 times dimmer than design, most of it indiscernible from noise. Data pipelines add delay, downlink windows, compression, calibration. By the time processed frames go public late November, the event is weeks old. The lesson is harsh but clear. The most critical moment may be hidden in the noise arriving too late to catch in real time. From mid-October through early November, the blackout rules. It's not conspiracy, it's geometry and safety. Ground telescopes won't risk optics in the glare. Space telescopes are hard-coded to avoid the Sun by 50 to 85 degrees. Parker Solar Probe and Solar Orbiter stare straight into plasma and fields. They won't pivot for a faint intruder at the edge of view. We lose direct spectra, images, radar, echoes, everything exactly when any maneuver would be most effective. So we prepare the after. Reacquisition plans lock. Pre-book time on Rubin, LSST, Hubble, JWST, ground arrays, citizen occultation networks. The telltales will hunt. A sudden outbound velocity drop that outgassing can't fake. Non-random fragment tracks. Polarization curves that swing in ways fresh dust alone can't explain. Falsifiability stays the rule. If the path matches predictions, if fragments drift randomly, if no anomalies line up, the story returns to nature. But if even one of those signatures lights up cleanly, the conversation changes for science and for everything downstream of science. Why the alignment matters still. Along the ecliptic, shallow approach maximizes Oberth opportunity. Discovered July 1 by the 3I Atlas survey in Chile, 3I Atlas is only our third confirmed interstellar visitor. Inbound speed over 200,000 km/h confirms it isn't bound to the Sun. Perihelion on October 20. NICE at 1.36, astronomical unit just inside Mars's orbital distance, says it should slingshot and slip away forever. But geometry is a whisper. A path so convenient for braking that it feels like a plan. Spectroscopists set the natural baseline. Cyanide steady, traces of H2O and CO, a vast coma sculpted by solar wind. Against that, we place the anomalies. Mass that doesn't tug, brightness that overperforms, rotation that doesn't tumble, alignment that plays the lane, speed aligned with opportunity. None alone proves anything. Together, they insist on a clean public test. Wait, reacquire, measure. That's how extraordinary claims should be weighed by the sky itself. Now the fork in the road. If 3I Atlas shatters at perihelion, we call it fragile and move on one more exotic comet surviving the deep and failing in the heat. If it sails through intact and nothing jumps in the outbound, the technological hypothesis quiets, but the alignment puzzle lingers. And if there's a step change clean, abrupt, beyond outgassing, then the third path opens. Someone, somewhere, used the Sun as an engine. That's when surveillance protocols escalate, not because of panic, but prudence. A captured interstellar object becomes the most valuable physics laboratory and the loudest geopolitical headline of the century. Until then, the instructions to ourselves are simple. Watch the outbound velocity, watch the fragments, watch the polarization, and let the data, not our fears, write the ending. This time, the silence isn't ignorance. It's the cost of doing astronomy near a star. 12 days to the furnace. A rare, low-inclination interstellar visitor, retrograde along our lanes, mass that doesn't tug, brightness that overperforms, chemistry anchored in the familiar yet arranged like a riddle and a blackout at the exact moment the truth might happen. On October 29, 2025, 3I Atlas reaches perihelion at 1.36 astronomical unit. On the far side of glare, our instruments will open their eyes and ask the only question that matters. Did it pass physics as usual, or did it choose? If you want the recovery windows, the raw astrometry, and the first verified post-perihelion frames the minute they land, subscribe now and turn on alerts. We'll publish the before vs after charts and the delta analysis the moment observatories release them. Until the sky speaks, we hold the line between wonder and proof, between chance and intent. And when 3i Atlas reappears, we'll be there, eyes open, measuring the difference between what nature allows and what intelligence attempts. So, do you think 3i Atlas is a natural anomaly, or is its perfect path along the ecliptic a sign of something more? If this cosmic mystery has you hooked, smash that like button to help others find this investigation. And subscribe so you don't miss the moment the truth emerges from the solar glare. We'll be here with the definitive post-perihelion analysis the second the data arrives.